today we shall consider finite state automata with output. Actually, we have considered this in the first class. In the first class, we considered the example of a serial adder. This was the state diagram. This is the state diagram of a serial adder, and the inputs are two binary digits 0 0, 0 1, 1 0 or 1 1. So, suppose you want to add two numbers, say 1 1 0 0 1, 1 0 1 0 1. What will be the output? 1 1 gives you 0 with a carry, and with carry this 2 zeros you will get a 1, 0 1 will give you a 1 without a carry, 1 0 will give you a 1 without a carry, 1 1 will give you a 0, there will be a carry which will be output in the next instance. So, you can see that this is the initial state with which you start. We do not mark any final state when we consider finite state automata with output. The first input is a 1 1, this corresponds to a no carry state and this corresponds to a carry state. So, when you get a 1 1, the output is a 0, but you go to the state q1 which is a carry state, that means there is a 1 here, and the next instance when you get a 0 0, you go to the no carry state, but you output a 1. In this state, a no carry state, when you get a 0 1, you output a 1, there is no carry, and you get a 1 0, you output a 1 and there is no carry. Now, in the no carry state, when you again get a 1 1, you output a 0 and go to the carry state, and in this state you are not getting any input, that is you have to consider it as 0 0. So, next instance, the last instance, a 1 will be output. Here the input symbols are pairs of digits. So, you can look at them as 0 0, 0 1, 1 0, 1 1. The output symbols which we denote by delta are either a 0 or a 1. Inputs are pairs of digits 0 or 1, 0 0, 0 1, 1 0, 1 1. Output alphabet is 0 and 1. So, this automaton works in such a way that when it receives some input, it outputs something. You can very easily see that this output depends on the state and the input symbol. So, in this example, the output depends on both the state and the input symbol. Sometimes the output may depend just on the state alone. So, that we call as a Moore machine, and this type of a machine we call as a Mealy machine. And let us define it formally. We also considered in the first class a one moment delay machine and a parity checker. Those machines also had output. So, we can look at the finite state automaton as an input output device, and generally when you look at it as a language recognition device, the input is accepted or rejected. Language acceptor, when you look at it as a language acceptor. For example, it can accept something like 0 power n 1, n greater than or equal to 1, a language like this. In this case, starting from the initial state, after reading some input, if you reach a final state, the input is said to be accepted. You can have a machine where the output will be 1 if you reach a final state, output is 0 if you reach a non-final state. If you look at it this way, even the acceptor can be looked at as an input output device. It outputs a 1 when the string is accepted. For example, here if you have a string like this, it will be outputting a 1 here, so that the string is accepted. If it is some other string like 0 0 1 0 0 something like that, it should not be accepted. So, at the end it will output a 0. In fact, at every state it will output something which will tell you that portion of that string is accepted or not. Now, let us go to the formal definition of a finite state automata with output. So, a FSA with output it is defined as M is equal to K sigma delta lambda q naught, as scriptable like this, where K is a finite set of states sigma is a finite set of input symbols delta is a finite set of output symbols delta is the state transition function. It is called the transition function. And it maps K into sigma into K. We are considering deterministic machine here. Lambda is the output function. Let us see what it is in a moment. We do not specify any final state because we are bothered about the output emitted at each instance of time. So, we do not consider a final state. Q naught is the initial state, Q naught in K is the initial state. Now, what about the output function? The output function can depend just on the state alone or on the state and the input symbol. So, in one case when the machine is a Moore machine, output function is K to delta, and in the case of a Mealy machine, the output function is, it depends both on the state and the input symbol. It is from K into K cross sigma into delta. Let us consider one example of a Moore machine and one example of a Mealy machine. It is not really very different in the sense that from a Moore machine we can go to a Mealy machine, and from a Mealy machine we can go to a Moore machine. We shall see that conversion also in due course. Let us consider one finite state automaton with input alphabet 0, 1, output alphabet 0, 1, 2, 3, 4. I will draw the state diagram. This is a Moore machine, Q 0, Q 1, Q 2, Q 3, Q 4. First, let me draw the transition functions 0, 1. Since the input alphabet is 0, 1 and we are considering a deterministic machine, from every node there should be an arc with label 0 leaving, and there should be an arc with label 1 leaving. So, from Q1 when you get a 0 you go here, from Q1 when you get a 1 you go here, from Q2 when you get a 0 you go here, when you get a 1 you go here, from Q3 when you get a 0 you go here, when you get a 1 you go here, from Q4 how do you reach? 1, 1, 0, 0. If you get a 0 you go here, if you get a 1 you remain in 1. Now, I have drawn only the transition function, the outputs I have not drawn. The output depends on the state. So, this is a Moore machine, we are considering a Moore machine. So, when the machine is in this state, it outputs a 0, I am drawing the output within the square. When it is here, it outputs a 1. So, the output for this state is 1, the output for this state is 2, the output for this state is 3, the output for this state is 4. You see the output alphabet is 0, 1, 2, 3, 4. Now, what does the output signify? You just take some string and check. I will take 1, 0, 0. What is this number in binary? What does this represent? What number does this binary representation represent? That is 4, right? So, 1, 0, 0, that is you reach state Q4 and output of 4. What does that mean? When divided by 5, the remainder is 4. Suppose I take the number 8, 1, 0, 0, 0. When divided by 5, the remainder is 3. Let us see whether you output a 3. 1, 0, 0, 0, you output a 3. Take some other number 12. What is the representation for 12? 1, 1, 0, 0. See what happens? 1, 1, 0, 0. You reach state Q2 and output a 2. 12 divided by 5 gives you a remainder 2. So, the here output really represents the remainder when divided by 5. You take the input as a binary string, it represents a number. When that number is divided by 5, what is the remainder? That is given as the output. Leading zeros are allowed. So, I am also allowing numbers like 0, 0, 1, 0, 0. This sort of a string is also allowed. So, I should forget about the leading zeros. You must remember that at each instance there is an output. For example, if I take 8, initially it starts in state Q0. After reading a 1, it goes to Q1. After reading another 0, it goes to Q2. Reading one more 0, it goes to Q4. From Q4, after reading a 1, it goes to Q3. So, this is the state sequence. What will be the output? The output initially will be 0, Q0 0, Q1 outputs a 1, Q2 outputs a 2, Q4 outputs a 4 and Q3 outputs a 3. So, the output sequence is this 0, 1, 2, 4, 3. We can see that when nothing is there, the output is 0. After you read 1, number 1 when divided by 5 gives you the remainder 1. Then after reading this, the number is 2. 2 when divided by 5 gives you the remainder 2. After getting one more 0, it is number 4, the remainder is 4. After getting one more 0, it is 8 and the remainder is 3. Suppose I were to get one more 1 here. What will be the number? 8 into 2 plus 1, 17. Q3 1 is Q2, output will be 2. So, 17 divided by 5 will give you the remainder 2. One thing you must note here is the input, if it is of length 5, the state sequence will be of length 6. If the input is of length n, the state sequence will be of length n plus 1 and the output also will be of length n plus 1. This is the case of a Moore machine. Okay. So, this is the way you define a Moore machine. I will keep this diagram and let us consider an example of a Mealy machine. This is an example of a Mealy machine. Of course, serial adder is a Mealy machine. And before going into that, let me justify this diagram. How are you justified in drawing a diagram? For example, from Q1 I am drawing an arc with label 0 to Q2 and from Q1 I am drawing an arc with label 1 to Q3. How am I justified in that? See, when you reach Q1, you have read a binary string which leaves a remainder 1 when divided by 5. So, the number will be of the form say 5k plus 1. Now, if you get one more 0, the number will be 2 times 5k plus 1 plus 0, which will be 10k plus 2. So, the number when divided by 5 will give you a remainder 2. That is why from Q1 there is an arc with label 0 going into Q2. On the other hand, suppose after reading something I am in state Q1 and I get the input 1, I go to Q3. How do I get this? This represents a number of the form 5k plus 1. When I get one more 1, the number represented will be 2 times 5k plus 1 which is 10k plus 3, and when divided by 5 it will leave a remainder 3. and that is why this arc is drawn in this manner. Like that, for each one of them you can justify why that arc with label 0 goes here, arc with label 1 goes here. For each state, by writing an expression in this form, you can see that you are justified in drawing this state diagram. Now, let me go to an example of a Mealy machine. You consider strings over the alphabet 0, 1, and if the string read so far, at the end you have 2 consecutive zeros or 2 consecutive ones, you output a yes, otherwise you output a no. The last 2 symbols read, if they are 0, 0 or 1, 1, you output a yes, Y symbol. If they are not, you output a N symbol. Okay. So, what is the output alphabet? The output alphabet is yes or no. So, the state diagram for that will be of this form: P naught, P1, P2. When I get a 0, output a no. When I get a 1, again I output a no. One more 0, the last 2 symbols will be 0, 0. So, I output a yes. From here, if I get a 1, the last 2 symbols are 1 and 1. So, yes. Here if you read any number of ones, the last 2 symbols will be 1, 1, 1, 1, etc. So, you will have a yes. But in this place, if I get a 0, again I have to start outputting a no, and if I get a 1 in this place, the output will be a no. So, this is an example of a Mealy machine. Note that the no or yes depends both on the state and the input symbol. In state P naught, if you get a 0, you output a no. In state P naught, if you get a 1, you output a no. In state P1, if you get a 0, you output a Y. In state P1, if you get a 1, you output a no. What will be the I will take some string. Suppose the input is 0, 0, 1, 0, 1, 1. What will be the state sequence? It will be P naught 0 is P1, P1 0 is P1, P1 1 will be P2, P2 0 will be P1, P1 1 will be P2, P2 1 will be P2. This is the state sequence. What will be the output sequence? When you get a P naught 0, you output a no, then P1 0, you output a yes. So, when the last 2 symbols are 0 and 0, you output a yes. Then P1 1 will be a no, P2 0 will be a no, the last 2 symbols are not the same. Then P1 1 will be no, P2 1 will be yes. Last 2 symbols are 1 and 1, so you will get a yes. Okay. So, this is the way the diagram is drawn. You can also look at it in a slightly different way. Consider a finite state automaton accepting strings corresponding to regular expression 0, 0 plus 1, 1. That is, this finite state automaton will accept strings if they end with 2 zeros or with 2 ones. Initially you can have any string. So, this is the regular expression for a set of strings which end with either 2 zeros or 2 1. Suppose I take this and construct the finite state automaton as an acceptor, what diagram will I get? Let me draw the diagram. A non-deterministic diagram will be like this, some q naught, right, q1, q2, zero 1, any string of zeros and 1 can be read, and it has to end with a 0 0, this is a final state, or it has to end with a 1 1. So, this is a non-deterministic diagram which will accept strings which end with 0 0 or 1 1. I can use the subset construction and construct the deterministic automaton. A deterministic automaton for that will be like this. I will use S naught, S1 etc. as state labels, S naught, S1, S2, S3, S4, S3 and S4 are final states, S naught is the initial state. If I get 2 zeros, it should be accepted. If I get 2 ones, it should be accepted, but after getting a 0, if I get a 1, I should go here, 0 1 1 will accept it, but 0 1 cannot be accepted. S2 and S1 are non-final states. In S2, if I get a 0, I go here. After getting 0 0, one more 0 I get, still it is a final, it will be accepted. If I get one more 1 here, still it will be accepted, but after getting 2 zeros or many zeros, if I get a 1, I have to go here. If I get a 0, I have to go here. Please note that this is a deterministic diagram. And how many states we have? We have 5 states. The non-deterministic one also we had 5 states. The corresponding deterministic automaton, I have not used the subset construction, you can use the subset construction and check, you will end up with 5 states. Now, is this the minimum state automaton? We know, given a deterministic finite state automaton, how to construct the minimum state automaton. Okay. So, is this the minimum state automaton, or do we have another automaton which has less number of states? Let us use the minimization procedure and check. Now, first you divide the set of states into final and non-final. So, 2 blocks you have, S naught, S1, S2 in one block, S3 and S4 final states in another block. Now, in S3, if I get a 0, I go to this, but from S4 if I get a 0, I go to another block. So, if from S3 if I get a 0, I go to this block, from S4 if I get a 0, I go to another block. So, this has to be split in the next step. So, you will get S0, S1, S2, S3 separate, S4 separate. Now, look at this, what are the 0 successors of S0, S1, S2? They are S1, S0, S1, S2 0 successors. They are S1, S3 and S1. S3 is different, S1 is in a different block, and S1 has a 0 successor which goes to S3. So, in the next step S0, S2 will be separated from S1, and S3, S4 are separate. Now, look at S0 and S2. What are the one successors? The one successor of S0 is S2, one successor of S2 is S4. They are in different blocks. So, this again will be split and you will get like this. So, this is the minimum state automaton. You cannot have an automaton with less number of state, a deterministic automaton with less number of states. But look at the same problem as a Mealy machine, where the output is yes or no. In fact, apart from yes or no, you could even say 0 or 1, does not matter, yes, 1 for yes, 0 for no. To make a string accepted or come out with an output yes, or if it is not of the form ending with 2 zeros or 2 1 with an output no, you require a machine which has only 3 states. But we saw that as an acceptor, when you want to accept strings ending with 2 zeros or ending with 2 ones, you require 5 states. This is the advantage of having a automaton with output. So, we have considered both the types, Moore machine and Mealy machine. Consider one example. Next, we shall see that they are equivalent. In fact, for a Moore machine, you can construct an equivalent Mealy machine, and for a Mealy machine, you can construct an equivalent Moore machine. Can you say a Moore machine is equivalent to a Mealy machine? First of all, you must remember that if the input is of size n, in the case of a Moore machine, the output will be of length n plus 1. In the case of a Mealy machine, the output will be of length n. So, there is no point in talking about the equivalence because the length itself is different. But you must remember that at the initial state there is an output in the case of a Moore machine. If we ignore that input, if we ignore that output, suppose I have this as the input, and in the case of a Moore machine it will be B1, B2, Bn, and in the case of a Mealy machine it will be some say C1, C2, Cn. If I ignore the first output, then can I say this can be equivalent to this if you construct it in a proper manner, and this can be equivalent to this if you construct in a proper manner. That is what we want to see. So, given a Moore machine, how to construct an equivalent Mealy machine, and given a Mealy machine, how to construct an equivalent Moore machine, and ignoring the first output in the case of a Moore machine. So, you are given a Moore machine k sigma delta delta lambda q naught. How will you construct an equivalent Mealy machine? The corresponding Mealy machine, you have the same set of states, same set of input symbols, same set of transition, the output symbols, same transition, but the output function will be different. Here it depends on the state alone, here it depends on both the state and the input symbol. The same initial state you have, but lambda dash, how do you define? Lambda dash is a function of q and the input symbol, the state and the input symbol. So, how do you define lambda dash qa? It is defined as lambda of delta qa. Delta qa is a state. In state q, if you read a symbol a, you go to a particular state, say q dash, the output corresponding to that state is the output for the pair qa. If we define like that, we can get the same machine. So, in this example, this is a Moore machine, let us change into a Mealy machine. How do you change? The outputs will now be defined like this, input, output. So, these outputs will not mark. So, when you go to Q naught, you are outputting a 0. So, from here when you go to Q naught, you output a 0. Similarly, from here you go to Q naught, so you output a 0. When you go to Q1, you output a 1. So, when you go here, you output a 1. When you go to this state, you output a 1. When you go to Q2, you output a 2. Here you output a 2. When you go to Q3, you output a 3. Here 3. When you go to Q4, you output the this is, I will write it as 1. So, suppose the earlier Moore machine, if I had say 9, the state sequence would have been Q naught, Q1, Q2, Q4, Q4, and output will be 0, 1, 2, 4, 4 in the case of a Moore machine. The output is of length 5. In this case, we have constructed the Mealy machine corresponding to that using this definition for the output function. Let us see what is the output. 1, first output we do not have in the case of a Mealy machine. 1, 1 0, this is 2, then 2 0, output is 4, then Q4 1, output is again 1. You get the same output ignoring the first output in the case of a Moore machine. So, you can see that given a Moore machine, you can very easily convert that into a Mealy machine. Similarly, we can also convert a Mealy machine into a Moore machine, but it is slightly more involved than this. Let me consider this example. Okay. So, now let us start with the Mealy machine now. The Mealy machine is given by K sigma delta delta lambda Q naught. Then the corresponding Moore machine. Now, the states are not just K, it is a cross product of K cross delta, and you have to, the input alphabet is the same, the output alphabet is also the same, and you have to define delta dash lambda dash. The initial state will be again a pair. The first component of the pair will be a state from K, second component will be a symbol from delta. This B can be any arbitrary symbol. Okay. How do we define delta dash? Delta dash, you have to have some pair QB A, is not it? The state is now a pair and the symbol red is a symbol. This will be a pair again. The first pair will be delta of QA and the second pair will be lambda of QA. The lambda dash now depends on the state alone. If you have a pair QB, the output will depend only on this pair and it is given by the second component of the state B. Okay. With this definition, let us construct the Moore machine corresponding to this. There are 3 states P0, P1, P2 and 2 symbols yes and no. So, there will be 6 states here, P0 no, P0 yes, P1 no, P1 yes, P2 no, P2 yes. Either of these states I can take as the input initial state, either of them I can take as the initial state. The transitions are drawn in this manner. P0, look at the definition, delta dash q comma b is, this is the input A, that will be delta of q a comma lambda of q a. So, in this case from P0, what state you go to P1 and what is the output? No. So, P1 n you must go to. So, from this or this, when you get a 0, you go here. From P0, when you get a 1, you go to P2 and output is no. So, when you get a 1, you must go here, and here also you must go here when you get a 1. From P1, when you get a 0, you go to P1 and S. So, when you get a 0, it will be like this, it will be like this. When you get a 1, you go to P2 and no. So, when you get a 1, go like this. From P2, when you get a 0, you go to P1 and no. From P2, when you get a 0, P1 and no. From P2, when you get a 1, you go to P2 and yes. So, 1, 1. So, this will be the corresponding state diagram of the Mealy machine. Now, let me check with one example. For an input say 0, 1, 1, say what is the state sequence in the case of a Mealy machine? This one, it will be P0, P0 0 is P1, P1 1 is P2, P2 1 is P2. This is the state sequence, and what will be the output? Output will be no, no, yes. This will be the output sequence. In this case, if you get a 0, 1, 1 starting from here, 0, 1, 1, okay. And I have not marked the output here, the output depends on the state and it is the second component. So, the output will be n here, the output will be s here, it will be n, I am drawing within a square, and it will be s, it will be s here, it is the second component of the pair. No. So, what will be the state sequence in this case? I shall write the state sequence here. Initially you start with P0 no. Please note that I could have taken this also as the initial state, does not matter, either of them I could have taken as the initial state. P naught n 0 is P 1 n, P 1 n, and what is P 1 n 1 is P 2 n, P 2 n, and P 2 n 1 is P 2 y, P 2 y, and the output sequence is the second component. So, it will be n n n y, but in the case of a Moore machine we have to ignore the first one. So, the output is n n y, here also the output is n n y. So, you get the same output. So, given a Moore machine you can construct an equivalent Mealy machine, and given a Mealy machine you can construct an equivalent Moore machine. Only thing is, in the case of a Moore machine you have to ignore the first output symbol. So, they are really equivalent models, and depending upon the purpose you have in mind, you either construct a Moore machine or you construct a Mealy machine, whatever you want. Okay. So, this is the main thing about finite state automata with output. Related to the concept of finite state automaton with output, we also have another concept, GSM mapping. We study about closure properties of languages. Regular languages are closed under intersection, complementation, union, etc. Similarly, context free languages. We also study something called sets or family of regular sets or family of context free languages. They are closed under GSM mapping. This sort of a statement will come across in some places. Mainly they are useful in finding the closure under homomorphism, inverse homomorphism, etc. What is a GSM? It is called generalized sequential machine. Generalized sequential machine. Here you have states, there will be an initial state, there will also be final states, and the transitions will be like IO. So, from this state Q you go to the state by reading a symbol, say A, the output will be a string. You have an input alphabet sigma and an output alphabet delta. A will be a symbol from sigma, W will be a string from delta, it can be epsilon also, it can be the empty string also. So, W belongs to delta star. Not only that, what you are interested is, when you start from the initial state and reach a final state, you read some input. What is the corresponding output? For example, I can have something like this. Say I have one state here, another state here. When I read a, I output I output 2 A's. Then when I read a B, I output 1 B, and when I read more B's, I output epsilon. Okay? And this I take as the final state, say Q naught, Q1. So, I have this diagram, this is a generalized sequential machine. Suppose I have a string A, B, B, B. How can I read this? A, B, B, B. So, what will be the output for the first A, second A it will be A, this B it will be B, for this B it will be epsilon, this B it will be epsilon. So, the output for this will be A power 4 B. In general, when I have an input a power n, b power m, for each one of the a's I will be outputting 2 a's, and the first b I will output a b, afterwards I will output an epsilon, and so this is the output for this language. This is say n m greater than or equal to 1, you can say. So, n greater than or equal to 1. If the input is this language, the output, it transforms this language into this language. A generalized sequential machine transforms one language into another, and mainly we see that if given a regular set, it will transform it into a regular set, given a context free language, it will transform that into a context free language, and so on. These gain importance in the case of Grosov properties, and also weighted finite state automata, which are useful for representing digital pictures.